Today's notes are on ionic and net ionic equations. And you might ask yourself, well, what does this have to do with solutions? Well, ionic and net ionic equations have to do with chemical reactions in solutions. So first, let's talk about what happens when we mix two solutions together. I have a simulation here that shows you exactly what happens. So as you can see on the left, in our PbNO3 when it's in solution, what actually happens is these ions separate. So we have lead ions and nitrate ions, and they're not together at all. And on the right side, we have potassium ions and iodide ions, and again, they're not connected to each other either. So what happens when we mix these two solutions together? Well, you would say that we should have a double replacement reaction happen where we get lead to nitrate, or lead to iodide, and potassium nitrate. But let's see what actually happens. So you can see that we have all these ions floating around. And when the lead ions combine with the iodide ions, then they fall out of solution. They connect and they fall out of solution. They're no longer separate. And it happens every time they meet up in the correct ratio. But you'll notice that the potassium ions and the nitrate ions are still loose. So they really don't participate in the reaction. So really the only product that forms is the yellow lead to iodide. And you see that at the bottom as a precipitate. And you'll notice in the formula that we're given that it's a solid. And the potassium nitrate is still aqueous, which means those ions are still floating around in solution. So how does this translate into different types of equations? Well, the different types of equations that we have are molecular, ionic, and net ionic. The molecular reactions or equations show the full formula. And you would think that by looking at a molecular equation that everything reacts. In an ionic formula or an ionic equation, they only show the ions. Show aqueous substances as ions. So this is a little bit more accurate, and then they also show solids as compounds. Solids, liquids, and gases as compounds. In the net ionic equation, they take this one step further and they eliminate what we call spectator ions. And the spectator ions, for example, were the potassium ions and the nitrate ions that didn't take part in the reaction, that were just floating there, and like I said, they really just didn't do anything in the reaction that we just saw. So the net ionic equation would have been just the Pb2+, and that's still aqueous, so we still got to write that, plus the 2I-, it's still aqueous, forming the Pbi2 solid, the yellow solid that we saw. So now we're going to take this and we're going to take it one step further and actually practice this. So what is the ionic and net ionic equation for this reaction? So right now, this is the molecular form of the equation. Everything is in compounds. It still tells us the state of matter, but everything's still in compounds, and it looks like everything's together. even though we know that when it's an aqueous substance, those ions really are not sticking together. So when we do the ionic, we're going to split all aqueous substances into their ions. So we know that potassium chromate is made up of K plus and CrO4 2- ions, or chromate ions. So how many potassiums are there though? There's 2. So we have to write 2K plus CrO4 2-, and these are both aqueous still. So we got to write down that they're floating around in solution. Plus, we do the same thing over here. Barium forms a 2+ ion, so it's going to be Ba2+, and that's aqueous. Plus chloride, the anion here, forms a Cl-, so that means we have 2 of them. So it's 2Cl-, again that's aqueous. And that's going to form 2K plus aqueous plus 2Cl- aqueous plus, because this is a solid, we don't split it up. It stays as a compound because those ions are attached and bonded to each other. So plus BaCrO4, and that's a solid. So that's our ionic equation. Now, what is the net ionic? In the net ionic, we're going to get rid of the spectator ions. So a spectator ion, when we're looking at it this way, is the substances that are the same on the reactant side and the product side, and they are exactly identical. So for instance, this 2K plus here and here, that's a spectator ion because it's exactly the same on the reactant side as it is on the product side. So we're not going to include that. The CrO4 2-, it's different on the product side, so we will include that one. So it'll be CrO4 2- aqueous plus barium. It's not the same here as it is over here on the product side, so we're going to write that down as well. And the Cl- is also the same right here as it is here, so we're going to not include that either. And then what we're left with on the product side is the BaCrO4 solid. So there's our net ionic equation. So we're going to get a little bit of practice at this, and we're going to write the balanced molecular, ionic, and net ionic equations for the above reactions. So we have to balance this out first. So we have this is our molecular, but we have to balance it out. So we're going to write out, so the magnesium is balanced here because we have 1 magnesium on the left side, 1 magnesium on the right side. And then on our product side, or on our reactant side, we have 1 H here and 2 H's on our product side. So we need 2 hydrogens there. And then on our chlorines, we now have 2 chlorines and 2 chlorines. So we're balanced for the molecular. So this is our molecular right here. Now for our ionic, we're going to take the things that are aqueous and split them up. So magnesium solid, it's a solid, so we're going to leave it as it is. Plus the HCl is aqueous, so we're going to split that up. So we have 2H plus aqueous plus 2Cl- aqueous is going to form, well, the MgCl2 is still aqueous, so we're going to split that up into its ions, so it's Mg2+ because magnesium has a 2+ charge, and that's aqueous, plus we have 2 chloride ions, so 2Cl-, and again that's aqueous, And then the H2 gas, because that's not aqueous, we just leave it as it is and copy it down. So there's our ionic. And then for our net ionic, we're going to get rid of the things that are our spectator ions. And those are the things that appear the same on our reactant side and our product side. So right here in our ionic equation, the Mg solid, well, we have Mg2 plus aqueous. That does not match exactly, so we actually need to include that. So we have Mg solid plus the 2H plus, H over here forms H2, so we do need to include that as well. So that's 2H plus aqueous. The 2Cl minus aqueous, well, we also have 2Cl minus aqueous over on our product side, so we do not include that. And now we're moving on to our product side. So the 2Cl minuses will cancel out. And what we're left with on our products is Mg2 plus aqueous plus H2 gas as our net ionic. And we'll move on to solubility rules. So what determines whether something is solid or not when it forms a product is the solubility rules. You don't need to copy these down because you've been given a copy of the solubility rules. And yours looks a little bit different than the one up here, but there's some basic things that are going to be the same. So when it refers to nitrates or acetates or chlorides or bromides or iodides, those are the anions. So these are anions. And anything with that anion is what it's talking about. So it can be any cation combined with that anion. So nitrates and acetates are generally soluble. And then they give you exceptions. There's no common exceptions for these, except you have silver acetate, mercury acetate, and lead acetate are moderately soluble. So that might mean that they're somewhat soluble, but mostly not soluble. And so soluble, that means that you're going to write it as an aqueous on your in your equations. Insoluble means you're going to write that as a solid in your equations. So other things to note, chlorides, bromides, and iodides are generally soluble, except if those are combined with silver, mercury, lead. So that gives you an idea of how to read your table. So we're going to move on to how to apply the solubility rules to example problems. So if we have this reaction, use solubility rules to determine which substances are aqueous and which ones are solids. So chlorides are soluble, and iron is not one of our exceptions to that, so that's going to be soluble, which means that we're going to write an aqueous. Hydroxides and alkali metals, all things with alkali metals are soluble, so that means that that's aqueous as well. However, most hydroxides are not soluble, and iron is not one of the exceptions, so that makes this a solid. And chlorides and things that have our alkali metals are also aqueous or soluble, so that makes that aqueous. Okay, so now we've determined which ones are aqueous and which ones are solids. And now we need to write the ionic and net ionic equations for this reaction. But before we can do that, we need to balance it, because this is an unbalanced reaction. So to balance it, we're gonna need 3 sodium hydroxides and 3 sodium chlorides. Now we can write these in ionic and net ionic form. So the ionic, remember for ionic, we're going to split up anything that has a Q on it. So we're going to have Fe3 plus aqueous plus 3Cl minus aqueous plus 3 Na plus aqueous plus 3 OH minus aqueous goes to FeOH3 solid plus 3 Na plus aqueous plus 3 Cl minus aqueous. And now we're going to write our net ionic. And remember, our net ionic is we remove those spectator ions. So things that are appearing the same on both the products and reactant side. So I see 3 Cl minuses over here, and I see 3 Cl minuses over here, so I'm not including them. I see 3 Na pluses here and 3 Na pluses here, so I'm not including them. And that leaves us with the Fe3 plus aqueous plus 3 OH minus aqueous forms FeOH3 solid. And there's my net ionic equation. And our last example, we're going to take everything we've done and we're going to actually include some stuff that from previous units back to reactions. So silver nitrate plus zinc chloride, because we need to predict the products of the above reaction. Well, this is a compound, silver nitrate's a compound, zinc chloride's a compound. We have two compounds, it becomes a double replacement reaction. And remember that in double replacement reactions, our cations switch places. So that means the silver pairs up with the chloride and the zinc pairs up with the nitrate. So that means we have silver chloride plus zinc nitrate. Then we have to write the molecular, ionic, and net ionic equations for the above reaction. And we need to include the states of matter. So the molecular is just writing these in molecule form, in formulas. So pause the video and go ahead and work on this. Welcome back. This is what you should have gotten for the molecular formulas. Silver nitrate is AgNO3, and because nitrates are soluble, it's aqueous, plus zinc chloride is ZnCl2, and again, chlorides are soluble. Most chlorides are soluble, and zinc is not one of the exceptions, so that makes it aqueous. Goes to silver chloride, which is AgCl, and while most chlorides are soluble, silver is one of those exceptions, so it is not aqueous, it's going to be a solid, plus zinc nitrate, and that is ZnNO3, and all nitrates are soluble, so we're going to put that as AQ. Now that we've got our molecular, we're going to write out our ionic. And again, you can pause the video here and see if you can do this on your own. Okay, welcome back. This is what you should be getting for your ionic. You should get Ag plus aqueous plus NO3 minus aqueous. And I'm realizing now that I did not balance this equation, so we need to balance it. So we need 2 silver nitrates and 2 silver chlorides. So that gives us 2 Ag plus and 2 NO3 minus plus Zn2 plus aqueous plus 2 Cl minus aqueous goes to 2 AgCl solid plus Zn2 plus aqueous plus 2 NO3 minus aqueous. Now we're going to work on the net ionic. And again, please pause the video and check your answers when you're done. Welcome back. And so what you should end up getting, we should be able to eliminate our NO3 minuses as well as our ZN2 plus. And so we should get 2 Ag plus aqueous plus 2 Cl minus aqueous goes to 2 AgCl solid. And because all of these are 2, we don't need to include that, so it should just be Ag plus Cl minus goes to AgCl. And if you have any questions, please rewatch the video, and good luck on your worksheets.